The total area corresponding to this partition is the sum of all the delta A sub I areas. So we can write the total area is A is approximately equal to the sum from I equals 1 to n of A sub I, adding up the n areas that we approximate in the same manner as this one interval. And of course that sum is then going to be the sum of the x sub I star times delta x. We didn't specify what I is. I could be any subinterval. I could be any number between 1 and n, corresponding then to the subinterval between x sub I minus 1 and x sub I. So that could be, if I is 1, that could be the interval from x0 to x1. If I is 2, then it's the interval from x2 minus 1, x1 to x2, and so forth. So this single expression applies to any subinterval. In the limit, as n approaches infinity or as delta x approaches 0, and these are equivalent conditions, given that we're assuming a uniform delta x, we get the sum from I equals 1 to n, well, the limit of this sum, the sum from I equals 1 to n of f of x sub I star delta x equals the integral of f of x dx. In the limit, the x sub i's essentially become x's, the delta x's become dx's. Now we're not doing an epsilon delta proof of this. This is something you should have encountered in first year calculus, just trying to recapitulate the whole process so that we can apply it to functions of many variables. Since the partition runs from x0 equals 0 to x sub n equals 1, the limits on the integral will be 0 and 1. Our specific function is 2 minus x squared, so that in this case we're integrating from 0 to 1 the f of x, which is 2 minus x squared, dx. Now, an antiderivative of 2 minus x squared is 2x minus x cubed over 3. This integral is the change in the value of the antiderivative function from x equals 0 to x equals 1. You're probably used to writing this out as something like 2x minus x cubed over 3 with a line and a 1 and a 0 here, and doing this mechanically, but I want to remind you that this means the integral from 0 to 1 of 2 minus x squared means the change in an antiderivative function. An antiderivative function is the change function for your original function. This gets us a little closer to the meaning of the fundamental theorem of calculus, and that's an important thing to remember. However you write this out, this is an easy enough integral. Evaluated at 1, we get 2 minus 1/3, which is 5/3. And evaluated at 0, we get 0, so that the area is 5/3. The integral is 5/3, and that corresponds to a total area of 5/3 on the interval from 0 to 1 beneath this graph. These should not be new ideas to you. Having completed first year calculus, you should be aware of this sort of process and the way that this process defines an integral. I've talked about it in terms of area. It can be talked about in much more abstract terms, and should have been, and we'll be talking in more abstract terms in this course as well. The area interpretation, though, is more familiar, and just to keep you or get you familiar with the whole idea, or to refamiliarize you with the process of setting up an integral, we've chosen to do this in terms of areas.